Hi everyone and welcome to today's webinar. I'm Sophia Ramsel and we'll be discussing multi-cluster observability and security with Linkerd and Kublr. Today's presenters are Charles Pretzer, Field Engineer at Linkerd, and Oleg Chunikin, CTO at Kublr. If you have any questions, please post them in the chat and we'll make sure to address them. Okay, let's get started.
Hello, I'll start. So thank you for the introduction, Sophia, and welcome everyone to this webinar. So what we are going to talk about today is multi-cluster observability and security with Linkerd and Kublr. And I'll start with Kublr as Kublr's vision to multi-cluster to cloud-native technology stack support in enterprise environments with modern requirements that modern companies set in front of cloud-native technologies. And then Charles will talk about how Linkerd works to help address multi-cluster observability and multi-cluster deployments on the application level. So let's start, and first a little bit of history about Kublr and what Kublr is, and our vision of multi-cluster, multi-environment cloud-native stack. So Kublr was born out of an initiative in a custom software development company to unify application delivery practices. So we developed a lot of projects in different environments with different customers, and at some point realized that they all have one common part: application delivery, and then maintenance, monitoring, operations. And we started looking for technologies and very quickly found out containers, Docker. It was all the rage back then. Started using Docker in most of the projects. Quickly realized that, well, Docker is great, but local. You have to manage distributed applications. You need orchestration, which is when Kubernetes came into picture, almost exactly or right after it was released publicly. And Kubernetes again helped solve a lot of problems with distributed applications deployment and maintenance, and again brought with itself a number of other problems. Who sets up and operates Kubernetes? How you solve operational aspects at scale when you have multiple clusters? And we also started feeling the need for multi-cloud hybrid deployments. And even if you are just in one cloud, you very quickly realize that one cluster is not enough. You need to manage multiple, even if it's just for dev and production environments. There are also other enterprise needs like governance, compliance that need to be solved, and this all needs to be built around your cloud-native stack and around your Kubernetes framework. And then this picture comes into play, cloud-native technology landscape, where you see dozens, if not hundreds of technologies that solve different pieces of this puzzle, but there is it's whole separate topic of which needs to be chosen to solve which task, how they need to be integrated, etc., etc. And this is where Kublr was born, essentially as a product that focuses on developers and operations needs in enterprise environments, and bridges the gap between cloud-native technology stack and enterprise environments with modern advanced requirements like multi-cloud support, hybrid support, governance, centralization of management of Kubernetes operations and applications operations. as well as, of course, security, reliability, performance, self-service for developers, configurations, etc., etc. This brought to life the vision of this reference architecture, which was implemented in Kublr as a product, so where you have open source Kubernetes and container technologies in the center, where you implement centralized infrastructure management for those Kubernetes clusters that you need to bring up and operate, where you have multiple operational aspects and security and governance aspects solved in form of integrated components like centralized log collection system, monitoring system, infrastructure management, API, air-gap deployments, security and airbag, identity management integration, etc., etc. And this is what I'm going to talk about today. In the first half of this webinar, the way we see centralized cloud-native stack management in an enterprise environment, and Kublr as a reference implementation of this vision. And I already talked about general 30,000 feet view of this. So digging deeper into this architecture vision, so one thing that was clear from the beginning is that this needs to be centralized. You very quickly realize you need multiple clusters, and you very quickly realize that you need to manage those clusters more or less from one control plane, from one pane of glass, single pane of glass. And that control plane needs to integrate the view of your cloud-native foundation at least, which means infrastructure management, image management, Kubernetes components and Kubernetes API endpoints, etc., etc. And this is why, so you almost always have to have some centralized management cluster or centralized management tool that manages multiple clusters around it in different clouds, potentially in different data centers. And this is what Kublr builds as its main components. Kublr platform, essentially a complex application which runs in its own Kubernetes cluster and provides you view and management of clusters under your control. So like this is the main view. You can see multiple clusters running in different environments, and this is again another part of the enterprise requirements. You never know that one single cloud will be enough for you, or one data center. So multi-cloud and hybrid deployments are more and more often a requirement for an enterprise that needs to be ready for future. And most probably you have projects that work with not just a project which deploys into Amazon only or into Google Cloud only, but projects that work across environments, or at least in hybrid environments with data centers and clouds. And you have view of your clusters. You can assess status of those clusters, hardware-related events. One of the important features is integration with role-based access control, because by itself role-based access control is quite an important, albeit relatively complex part of your cluster separations and management, and you want to be able that your management platform can integrate with this part of Kubernetes functionality. Another important aspect of this centralized management architecture is openness and future readiness, so to say. And for that, what we found works best is separation of concerns. So, and let me switch to a different slide, which talks, go back a little bit to a slide which looks at the platform as a whole. It's great when your Kubernetes management tool also includes some CI/CD features, for example, or it includes a form of service mesh. But you very quickly realize that in more or less complex environments, the built-in features may not be necessarily enough for your team, and for mid-size, larger enterprises, larger companies, your teams, because one-size-fits-all approach rarely works at scale, and now you may face a question of how to accommodate requirements of different teams in terms of CI/CD, for example, or ability to implement using different serverless technologies, for example. And from that perspective, it's very important that your platform, even if it has features like CI/CD, for example, keeps the platform layer, Kubernetes layer, open and ready to be used with other CI/CD approaches and tools. So, and this is what we implement again in the platform, focusing mainly on operational requirements of operations teams that need to deliver Kubernetes and need to make sure that this Kubernetes is compatible and can work with any tools that are compatible with Kubernetes. Another important requirements for enterprises in terms of cloud native stack usage is observability, and this is part of the one of the main subjects of today's webinar. And so Kubernetes is well suited to provide sort of very high level of observability for your applications. You're probably aware of various log collection add-ons and monitoring add-ons that can be run in Kubernetes clusters. Very well-known stacks include Prometheus, Grafana, Alert Manager for monitoring, ELK, Elasticsearch, Kibana for log collection. But when you start digging deeper, you quickly realize that in most cases it's a local in-cluster monitoring and log collection, and centralized monitoring where you have access to metrics, for example, from multiple clusters, is something that you need to build on top of that, which is why we see that centralized monitoring and log collection infrastructure and stacks important part of the final vision for cloud native platform, and which is why we are building it into the platform, the Kublr platform. So, and the idea again is to use open components so that you don't have to invent anything new when you deploy your application into that stack. Your application can just expose well-known interface for Prometheus to collect metrics, and whether you are running it in your own cluster which runs local Prometheus, or it runs in a Kublr provisioned cluster, those metrics will be collected exactly the same. But in case of Kublr or this integrated cloud native platform, you'll also be able to see those metrics running into your database from different clusters, and you'll be able to perform cross-cluster, cross-environment analysis, which may be very important again if your application is distributed across different regions, across data centers and the cloud. There are a number of scenarios where this is required, starting from high availability, scalability, and cost optimization reasons why you may want to have part of your application, for example, in the data center and part in the cloud. So, and the same is true for log collection. Again, you want to see your logs and you want to analyze them across environments potentially if you are managing multiple clusters and multiple environments, and you want to have them in a single database ready to be analyzed across clusters. So Kublr implements it through ELK stack, where ELK stack runs as a part of the control plane and collects logs from all clusters under its management. Other ways of implementing this may be by using external log collection systems, like sysdig, for example, which need to deploy agents into every cluster under your management, but in the end they would accumulate logs and metrics under the same cloud available system. And of course, important part of multi-cluster management and observability is access control, security, and multi-tenancy, at least intra-organizational multi-tenancy. Yeah, so security may mean a lot of things and different things for different organizations, and it starts with the fact that some organizations may not be comfortable with software as a service for infrastructure components, infrastructure management components like this, because with multi-cluster management, Kubernetes essentially becomes your infrastructure. It allows you to unify management of your infrastructure and presentation, most importantly, presentation of that infrastructure to applications and application developers. Now, instead of figuring out how to deploy their applications to Google Cloud and AWS, people would just develop a Helm package that will go unchanged into both clusters, whether those clusters are in AWS, Google Cloud, or in the data center. But the backside of this comment, flip side of this coin, is that now, as your Kubernetes is your infrastructure, it becomes a critical piece of software that you want to keep control over. So this control plane should be able, at least in principle, run in your environments, whether it's a data center or your cloud account. And this is again what Kublr implements, because it's not a software as a service, it's a product. But then after you are running this platform, you realize that you have multiple teams, multiple projects, and not all of them should be allowed to see each other's environments for one reason or the other. And you need some form of inter-organizational multi-tenancy, which again implemented conceptually similarly to Kubernetes namespaces. So we may have different spaces, each of those spaces hosting a group of clusters. So like here we have a space called demo where we have 5 clusters, and then there is another space called Linkerd where we have 3 clusters ready that Charles will use to demo Linkerd capabilities in terms of multi-cluster management. And of course, it's important that those spaces can be access to those spaces can be restricted, which can be done through, again, role-based access control management features. And your enterprise users need to be able to sign in to this system, at least as users of those clusters. So most probably you also need integration with enterprise identity management system. So integral part of any platform or stack like that must be ability to integrate with identity management systems, which is in Kublr implemented again by an open source component identity broker based on Keycloak, which runs as a part of the control plane, and out of the box it just provides user management features. So you see there is Charles account, there is admin account, you can manage groups of users with Keycloak and their access rights. But in more advanced scenarios, in most cases when you have a production deployment, you would also use it to integrate with Active Directory, for example, or LDAP server, wherever you are storing your user accounts, or integrate it with SAML or OIDC based identity provider, so that your users will be able to log in to the platform and log into clusters managed by the platform. Okay, having said that, I think the next question is, well, now I have my clusters running. I have my clusters running across environments, and I have monitoring metrics collected from them. Now I want my applications to be able to be deployed into those clusters and to be able to talk with each other. And this is where higher level software like service mesh, Linkerd, for example, comes into play. And this is where I'm ready to pass the back to Charles, who will talk about how Linkerd helps solve this problem with multi-cluster communication capabilities.
Awesome. Thank you, Oleg. It's always, I think I learn something new every time I see you go through that demo, so that's really great. So yeah, you're right. Now that we've got our clusters set up, the next step is to get an application up and running on them. And in addition to that, we want the application to be able to communicate across those clusters. And we'll talk about the reasons for that, and we'll go over why somebody would want to do this. So I will start to share my screen here, and we can jump right into that. Okay, so multi-cluster with service mesh, or multi-cluster service mesh with Linkerd. So I'm going to give you a brief overview of the service mesh, just like Oleg gave you an overview of Kublr. We'll talk about some multi-cluster concepts, and then we will actually dive into the terminal and deploy an application and see it working in real time. The service mesh overview, when we talk about a service mesh, it's really all about the distributed application. And here's a very simple distributed application where it's not cluster specific, it's not service specific. We have 3 pieces of logic that communicate with each other based on requests from the external world. And in a real world application, what we see is that we have multiple services that are not only communicating with each other, but also communicating with databases, external APIs, maybe some internal APIs, anything that you can think of. Our applications are complex, and that's where a service mesh comes in to help out with this complexity and to understand the performance and what we call the golden metrics of the application and how each of the services relates to each other. So again, we're talking about a real world application here, and even this is a simplified version. I've spoken with folks in our community and people, companies that are using Linkerd, and their applications are much more complex than what we see here. And one of the things that they found is they're using their application is in this diagram, this is all happy path. If the application always worked like this, then there would be no need for people to be on call or even for something like a service mesh. But the reality is things go wrong. The database could come under a tremendous amount of load or could be locked transactionally. And so that affects the application's response times and performance. Our external APIs could go down. They could just be unavailable. Oftentimes, external API providers will provide rate limits. And so let's say you get a spike in traffic one day and all of a sudden you've hit those limits and they begin to deny those requests. And, sometimes we roll out new versions of code, especially in this world now where we're automating and doing real-time rollouts, testing in production. Sometimes we roll out some code and it just doesn't perform the way that we expect it to in production. So what that means is there are these points of failure or points of latency that we need to understand and know about. And that's what the service mesh provides. It does so by using a sidecar proxy pattern. And so specifically Linkerd, what this means is we have a proxy that's built using Rust, which is a language that is memory safe and very, very highly performant. So the Linkerd proxies themselves take about 10 megabytes of memory and are very lightweight and redirect the traffic, actually send the traffic directly to the services themselves within a Kubernetes context, which we'll see in the same pod, which is the same thing as communicating over localhost. So when we look at that original diagram that we saw on the first slide, all of our components, services A, B, and C, were talking directly to each other. But now we see that the proxies are intercepting that traffic, and they are then routing it or proxying it to those services, which still enables the proxies or the services to communicate with each other. But we now have a way to do some really interesting things and get some really interesting information from those proxies. The second part of the service mesh is the control plane. And so the control plane is a set of components that are used to configure each of the proxies. So the proxies themselves, because they're so lightweight, they are pretty simple, but they need some configuration. They need to know how to send requests and where to send requests. And we'll also see that they need to be secure. And so the control plane maintains all of that configuration so that when a proxy is injected into a service or into a pod, the control plane manages the configuration of that proxy for that specific service. So Linkerd provides 4 key concepts that we think are crucial to any service mesh, and that's observability, security, reliability, and traffic management. And each one of those is, we'll see throughout the demo, we'll see how each of those is implemented. For the observability piece, Linkerd provides us with the golden metrics, which are success and failure rates, as well as latencies between the services. We can also see the traffic in real time through one of the Linkerd commands, so that if there is an issue between 2 specific services, we can the command that we use is called tap. We can tap that traffic, and it is a lot like TCP dump if you've ever used that before. For the security piece, Linkerd enables mutual TLS by default. What that means is that when the proxies are managing the traffic between 2 services, all that traffic is encrypted without any extra work done by the developers of those services. So it's transparent. And then reliability makes sure that the services are available. So this means implementing things like retries and timeouts, and most importantly, it means load balancing. And so if you recall back to that diagram where you have multiple instances of a single service, you want to make sure that each of those instances of the services get an equal amount of traffic, or get the appropriate amount of traffic. And what that means is some services may just by nature be slower than others, some instances. And so Linkerd inspects the latencies of each of the instances of a service and then determines which instance to send the next request to based off of those latencies. And finally, we have traffic management, which is sending portions of traffic to different instances of services. And this will make more sense in the context of canary rollouts, blue-green deployments, something where we want to be able to send the same traffic to different versions of services. So let's take a look at each of those. As I mentioned before, all of these features are implemented transparently with Linkerd. So we install Linkerd, we get to see the metrics straight away, we get the security straight away, and as I go through the demo, I think you'll see how this is, it actually happens so fast that it doesn't seem like anything's going on. But the main takeaway here is developers no longer have to implement, to write code for things like mutual TLS, which is pretty difficult. They also don't have to worry about doing things like writing their own load balancing algorithms or retry mechanisms. So it sounds like magic, and it kind of is, but we're going to dive under the hood and show you like the actual way that these things work. So let's talk about multi-cluster concepts. Initially, Linkerd was designed to work on a single cluster, and recently with version 2.8.0, we began to support multi-cluster. And what that means is we have 2 clusters, and we want them to run the same application and communicate with each other across the public internet. And so there, as you can imagine, there are some things to take into consideration there. So how does Linkerd multi-cluster? There are lots of ways to connect the clusters, but the Linkerd approach is to be secure. So as I mentioned, everything happens over mutual TLS. It's Kubernetes first, so remote services appear as Kubernetes services on that cluster. And I think that'll, well, actually, I'll just say when we make a request to a cluster in one region, the implementation is designed in such a way that it doesn't matter where the actual request is served from. If it's served from a different cluster, that's totally fine. It's transparent. There's no single point of failure because Linkerd runs on every single cluster. And I have a slide coming up that'll make that apparent. Transparency we discussed. And again, it's network independent. So the only requirement is connectivity between the gateways of the multi-cluster approach. So again, one of the main design principles of Linkerd as a service mesh is to just be simple, to have a great user experience, and to just work. And we'll see how that happens. So when we were designing the multi-cluster approach, the implementation, we talked with a lot of our users, our community, and companies using Linkerd, and we asked them, actually they asked us, do you support multi-cluster? And we said no, but if we did, what would you use it for? And these are some of the answers that we got back. We got the traffic migration, which leads into things like canary deployments, blue-green deployments, and being able to use different environments like production and stage and testing. And that also means that there's the ability to use different availability zones. And so if you're a company that has an international application, or even an application that is, let's say, in Europe, and you want the performance to be as good in Italy as it is in the UK, then what you need is to be able to have data centers or services running in each of those countries so that the traffic from a user in the UK goes to that data center in the UK, and the traffic from a user in Italy goes to a data center in Italy. And this just makes the performance of the application very snappy, and the users don't have to wait, which we all know is something we want to avoid. And another reason that folks told us that they would use multi-cluster is for failover. Now, failover would be if one data center goes down, they want to seamlessly shift that traffic to another cluster. And so that's what one of the things that multi-cluster allows for. Linkerd connects the clusters in a very secure way. There's a command that will run when we do the demo where the cluster, we have the source and the target. And throughout this demo, the target will be the east cluster, or in this case, I'm calling it GCP. And the cluster in the west will be AWS. So not only are we doing multi-cluster, but we're doing multi-cloud thanks to Kublr. So when I link the clusters, the GCP cloud will, I think I got that backwards. The GCP cloud will create a kubeconfig secret from the service account, store it in the east cluster, the target cluster, and that way there's a component called the service mirror, which I'll show you in just a second, that then can communicate back to the API server in the source cluster, so that whenever there are service updates, whenever there's a status update, that server can know about it. And that's crucial because if a service fails in one of the remote clusters, we want to stop sending traffic to it. And this will allow us to do that. Or if a new service is deployed or more instances of a service are deployed, like there are more pods of a single service, then that means that we want to let the API or the other cluster know that there's now more availability of another service altogether as a whole. So let's talk about security. It's really important to understand that the Linkerd gateway components communicate over the public internet. And it's funny, I was just debugging an issue with a user of the multi-cluster configuration, and their clusters couldn't talk to each other. And it turns out their IT had set up their clusters in such a way, being very secure, that no public IP traffic was allowed. And so that step by the IT team was a layer of security on top of what is already available in Linkerd. So the gateways communicate with each other using certificates that are provided during the install time. And when we go through the demo, I've already created the certificates, but I'll show you when Linkerd is installed, how those certificates work. And this, again, is an extension of the mutual TLS that I talked about. So when the gateways communicate with each other, they send over that certificate, the secret material. And when the other gateway receives that request, if the secret material doesn't match or is invalid, the request will be just outright rejected. So what that means is if there are folks who are aware of your public IP address for your gateway, and they're trying to do something malicious or even accidentally just trying to poke around in there, those requests will be rejected because presumably they will not have the secret material. So this is what the multi-cluster installation looks like when we're all said and done. And this is part of the demo that I'm going to go through. So the test namespace is where our application namespace lives. So if you're going through this on your own and you're using your application, you'll have a different namespace and some different services in there. The Linkerd namespace is where the control plane lives, which I mentioned. It configures each of the proxies as they're deployed, and also maintains the health of the components within the control plane. The Linkerd multi-cluster namespace is what was added in Linkerd 2.8, and it adds those two components that you've heard me allude to in the last few minutes about the Linkerd service mirror and the Linkerd gateway. So these are two deployments, again, one that communicate cross-cluster, that provide the updates based off of Kubernetes events, and that also route the traffic between each of the services. And we'll also jump into a traffic split test. So what we're going to do when I mentioned the traffic management part, we'll split the traffic from requests coming into the GCP cluster, the West cluster. We'll split that in such a way that half of the traffic is actually routed to the cluster on AWS. So we do that through the service mesh interface spec, which defines the traffic split custom resource definition in Kubernetes. And it's the way that we can accomplish a truly distributed application across multiple clusters. So with that, let's jump straight into the terminal and get this demo going. You'll see here that I have two clusters. I have the AWS cluster and the GCP cluster. And I've written several scripts to expedite the installation process. All of this stuff is available on the Linkerd website. There is a tutorial for using multi-cluster. I assure you that I am not doing anything sneaky here. So let's take a look at the pods in the cluster. And let me see if I can make this a bit more readable. There we go. So we can see here that we've got the Kublr pieces for the control plane that are managing the logging and the configuration for Kublr. We've got the Kubernetes dashboard and just the Kubernetes, the kube system components. And that is in the, let's see, that's in the, oh, sorry, I'm using Azure, not AWS. So this is the Azure cluster. If I get the pods in GCP, we see the same thing. We've got the Kublr pieces, we've got the kube system components. So there's nothing, these are clean, fresh clusters that were installed of Kubernetes. So the first script that I'm going to run is the installation script, which installs Linkerd. So like I said, this is just going to go run the Linkerd install command, and it's going to use the context names of the clusters that I've created. One thing I want to show you is the Linkerd CLI, which I already have installed, shows me that the client version that I have locally is 2.8.1, and the server version is unavailable because Linkerd is not installed there. So let's install it. This is going to go through, it runs the Linkerd install command through the command line interface, and which creates the cluster role bindings, the service accounts, the services, the secrets, the config maps, the deployments, everything that the Linkerd control plane needs to run. So this is what we're running now, is the deployment for the Linkerd control plane. So the Azure control plane is deployed, and this is the Linkerd check command that's running now. So once we do Linkerd install, we run Linkerd check, and this goes through and verifies that all of the resources were deployed properly and that each of the components in the control plane is up and running. So you'll see here that it's iterating over, just waiting for each of the components to become ready. I could break this right now, but here we go. And we're just waiting for Prometheus to become ready. That'll take just a second. Linkerd is deployed with both Prometheus and Grafana as part of the control plane. And this is similar to how Kublr uses Grafana. We want to use as many open source projects as we can, as many CNCF projects as we can, so that we don't have to write anything new, but also because Linkerd is designed to be a service mesh and does service mesh things. Prometheus is designed to be a metrics collector and aggregator and manage time series data. And so there's no need for us to go and try and do that when Prometheus is the experts in that. So we see that everything is running as we expect it to. Now, if I look at the pods that are running in each of the components, or sorry, each of the clusters, we can see now that a Linkerd namespace has been added. And so we'll see the same thing in the GCP context. And same thing. So now we've got Linkerd up and running. This is great. This is exactly what we want. So the next thing we're going to run is number 2, which is to install the multi-cluster components. So let's do that. So the multi-cluster components install much faster because there are only 2 of them. And in this script, once the Linkerd install multi-cluster command is run, it goes and checks and waits for the deployments to start up. So right now we're waiting for that gateway component to start up, and that'll take just a second. And in the next step, so we have a Linkerd check command here specifically for multi-cluster. And what this is adding is checks on the multi-cluster resources in the cluster. So we see the deployments are Linkerd Gateway, Linkerd Service Mirror, and we have a service here now that is a load balancer type. And eventually this is going to give us a public IP address, and that's how the 2 gateways are going to communicate with each other. This is the part where I am supposed to talk slowly so that the IP addresses, public IP addresses, can be provisioned. But let's see if, let's actually look at the pods in the cluster again. So we have Kube system, the Kublr pieces, the Linkerd namespace is there, and now we see some new pods in a new namespace called Linkerd Multicluster. And we should see the same thing in GCP, which we do. So I think I stalled long enough. Let's see if we can find if our IP addresses have been provisioned. One thing that I've learned throughout doing this is that different cloud providers take different amounts of time to provision IP addresses. So, oops, I spelled that wrong. There we go. Okay, good. Everything is provisioned. So this is where we now actually connect the clusters. Right now we could deploy our application on both clusters and they wouldn't communicate with each other. By linking the clusters, we're making the Linkerd service mirror component aware so that when we deploy services and we deploy them, what we're going to do afterwards is export the services. So we deploy our services and then we export them. That means that we can now send that traffic across cluster, which is the really, really exciting part. So let's see, I think I just ran, yeah, link clusters. So let's look at that one before we run it. So again, this is running the Linkerd multi-cluster link. So I can see this script is actually going to fail because I need to change it. So let me change something real quick. I'm glad we looked at it. Okay, good. In fact, the only, oops, that's not right. The only command I actually need to run is this one. But we'll, yeah, here, we'll make sure that, great, okay. So we're only going to run one of these links. There we go. So the credentials were created. We're doing a check again to see the status, the gateways. And so we see that the GCP cluster can now, is aware of a Linkerd gateway. The AWS cluster, or the Azure cluster, is aware of a gateway named GCP cluster, and it's alive, it's available. If we go look at the pods if we actually look at the logs of the service mirror, we will see that the service mirror has established communication with the Linkerd gateway on the remote cluster. Okay, so lots of logs here, but here's a really good one to see. We've got a probe manager that continuously checks to make sure that the gateway is healthy. And so it says, I've communicated with this cluster at this address, and I got a good response back, so it's healthy, everything's good, we can move on. So the next step is to install this test application. So there's a gentleman named Stefan Prodin at Weaveworks who has written a fun application for testing different versions of a service, and so that's called PodInfo. We're going to run that now. One of the things that I want to do before we get started there is show you. Actually, no, we'll just do it. We'll look at the Linkerd dashboard in just a second. So it's installing a front end, which is just a simple UI that connects to this PodInfo service. When these are up and running, again, we'll have our application, the PodInfo application running on both clusters, but they're still not, the services themselves are still not communicating. The clusters are communicating through the Linkerd gateway. The next step that we're going to do is to export the services. And so by exporting the services, we're creating in the AWS cluster, the cluster named AWS, we're creating a new service that has endpoints in the remote cluster. So I think that'll be, these deployments will start eventually. I'm just going to break this so that we can take a look at the application. So here we go. This is on from our AWS cluster. We see that we're getting a response. So the application is running, which is exactly what we want. I think, yeah, give me 1 second here. I'm going to move some things around. Okay, good. That's all I needed to do. And so we're seeing the request there. We also, in that script, ran a curl command against localhost. So we're port forwarding to port 8080. And so that application will give us a JSON response. It'll also give us the HTML response that we see here. Okay, good. So our services are running. In fact, we can go, let's see, we'll use, in the test, actually, let's specify which context we're using. So in the test namespace, we have front end and PodInfo pods that are running, or services that are running, and they are not accessible from the external application. Oh, I broke that command too early, so let me go back and run this installation on GCP real quick. So we're going to do, oh, I see why. Great, okay. Nope, that's the export. Okay, sorry about that. My scripts are a bit out of date here, so we're going to do kube control GCP apply -k GCP. There we go. Great. Okay, so now if I look at the services in GCP, I should see them there, and in AWS as well. So everything's good. So we have services running in both applications, and we can do the same. If we look at the pods again, I now have the test namespace with some pods running in one context, and if we look at the other context, the other cluster, we'll see that as well. So test with a couple of pods, they've been up for about 30 seconds, which is great. I saw one thing that I need to change inside of that next script that I want to run. And so this script, we can talk through it while we edit it, if I can type and talk. Okay, so this script is going to call the Linkerd command to actually export the services. And so the main thing to know about here is when we export the services, it's going to create that service in a service in the current context, in the GCP context, to connect to a service in the AWS context. And so we'll do, first I want to show you, again, the services, and this is in the current context. And so we'll run, export the services. So now, if we do service -n test, we see something interesting here where we see a pod info service that was created with the name of the other context appended to it, which is what we want. The interesting thing is if we look at the pods, we see that we still have the same two pods there, two instances of that pod info. So again, let's get the endpoints. And we can see, oops, use the right namespace. So we can see that there's some endpoints and that those are referencing the gateway IP address of the remote server. So for the local services, those are running, they're using pod IP addresses in the local cluster. For the remote services, they're using the public IP address in the remote cluster, which is really cool. Okay, next thing we're going to do is start looking at what these services are doing. So Linkerd comes with its own dashboard, and we can also look at the statistics from one of the services. So we'll run this command. So the first thing we see from Linkerd stat is that the services from the AWS context are running with these latencies. And what we really wanted to see there are the services from the GCP context. And when we look at those, we see that there is, again, the same pod info services. There are two pods there, and we're seeing some different latencies through those. So the performance difference that we're seeing is because the requests are being made across the public internet. So we see much faster times through the local services. This is the Linkerd dashboard, and it has everything that we want to see from our test services. We've got a service topology here, and we can see that there are two pods for the pod info service that are showing good response times. And we can also take a look at the Grafana dashboards. And the Grafana dashboards are generated per service. And so we can see that for the deployment pod info, we get latencies, request rates, success rates. Other dashboards that are distributed with Linkerd are the Linkerd Health, which shows you the control plane health for each of the services, each of the components of the Linkerd control plane. So here we see the service mirror, which is doesn't have any connections at the moment. But there are also the pieces like Grafana, which we're looking at now, and we see that, oh, look, all of a sudden there's some open connections. And because we're using Linkerd multicluster, there's a multicluster names or dashboard. And as Linkerd collects the metrics, we'll begin to see these stats go up. Right now, it's still collecting the metrics. The gateways haven't been detected yet. So that's the dashboard. These are the user interfaces for using Linkerd. You can also use the command line interface, which is pretty powerful. And at the end of the day, the command line interface provides all the same information that the dashboard does, just you can use it through your terminal. So the next thing we want to do is a security test. And as I mentioned before, we had some certificates that were created, and when we installed Linkerd, we issued those certificates to the clusters, and those are now used for not only for the proxies within in the cluster, but also for the connection between the clusters. So let's see what's going on with this. AWS, Linkerd Gateway. So it's not getting anything back from this. That's okay. We will bail out of that one because I want to get into the traffic split. So traffic split, and this will show us the actual cross-cluster communication. So the traffic split, I need to edit this file. We have, if you recall, we have podinfo and podinfo GCP. So the traffic split is a CRD defined by the service mesh interface specification, which is an open source project that is also part of the CNCF. And what it does is it allows you to weight traffic. These are weights. As requests come in, the proxy will determine the weight of that request and send it to where the service that it should go to. So right now we're saying send 50% of the traffic to podinfo and 50% of the traffic to podinfo GCP services. Okay, so if I apply that, and just as a reminder, we'll look at the services. We have podinfo, podinfo GCP. And if I do Linkerd, actually, yeah, that's right. So we'll look at the statistics in the AWS cluster, and we should see that, yeah, okay, so we see that there are 50% of the traffic is going to podinfo GCP. Oops, I'm getting a little bit of feedback here from the application, but this is a good thing to have happen. So again, this podinfo test is sending requests on its own. It continuously is updating itself. And so what we should be seeing is that this switches from AWS to GCP. So let's do, we want to do Linkerd dash. So there's no traffic found in the GCP, but we should be seeing some through the AWS one. So it looks like traffic isn't being routed across, which I'm not sure why that's happening, but let's see. There is, okay, let's see if this gives us some info. So we are not getting any traffic going across. Okay, well, I've got a gateway timeout. So this is the problem with live demos. Sometimes they just fail on you. So we'll bail out of that. But as you can see, we've got a few simple steps to set up Linkerd multicluster. When the clusters are connected, we begin to see the traffic communicating directly with each other, and the main takeaway there is that we see those latencies for the remote services, the target services, is usually much higher than the latencies, is always much higher than latencies for the local services. So with that, we'll do a bit of Q&A, or we can do Q&A afterward. But this is my contact info. You can reach me anytime on Linkerd Slack, and please check us out.
Awesome. Thank you, Charles. So we do have a few more minutes, and I have a few questions from the audience. We can go ahead and get started with those if that's okay. The first one is, does Linkerd run on any Kublr managed cluster?
Yeah, it will. So Linkerd is designed to run on Kubernetes anywhere. So in all of the tests that Oleg and I have run together, Linkerd will run on any of those clusters for sure.
Yes, and the idea behind Kublr, one of the ideas behind Kublr is that it deploys fully compatible Kubernetes clusters using upstream open source Kubernetes components. So on Kublr's side, there is a promise of compatible CNCF clusters.
Awesome. The next question I have how often do you see people using multiple clusters?
I think Oleg can answer that better than I can. We get asked about it a lot, but yeah.
So essentially, I think our view is a little bit biased because people come to us when they realize that they need to manage multiple clusters, and it's difficult to do it in-house. So we see them quite often. So and there are many reasons why you may need to do that, starting with just separating environments. Dev and prod is never a good idea to be run in the same cluster. Maybe using multiple regions for the same cloud for high availability reasons. Maybe using multiple clouds because different teams are working with different services in those clouds. Or again, you want to have vendor independence for future. If you are a large retailer, for example, some of them had concerns when Amazon moved into retail business, so they started diversifying even to that degree. So there are a lot of reasons to go multi-cloud and hybrid nowadays.
Awesome. It looks like our last one, I believe, is directed towards you, Charles. Does Linkerd multi-cluster require extra security?
No, and so that's funny that question came up because, again, I was working with somebody just yesterday who their IT team implemented extra security, and again, rightfully so, because you don't want to expose public IP addresses in all cases. But from a Linkerd perspective, because we're using those mutual TLS certificates to communicate between those two clusters, yeah, there's any security on top of that is extra, but it's not necessary for Linkerd clusters to communicate with each other.
Awesome. Well, thank you so much, Oleg and Charles. That looks like all we have from our audience today. Thank you for joining, and we hope to see you all next time.
Yeah, thank you.
Thank you.
Take care.